I'm Kevin Yang, a fifth-year PhD student in mathematics at Stanford. My advisor is Professor Amir Dembo, and my research focuses on small-scale fluctuations in random growth with an emphasis on the Kardar-Parisi-Zhang, or KPZ, equation. In 1986, the physicists Kardar, Parisi, and Zhang investigated small-scale fluctuation statistics in random growth, including the surface of a bacterial colony, the crack formations in rocks, the structure of crystals, and the propagating fronts of coffee stains. Through physical heuristics, they predicted that small-scale fluctuations were universally described by the KPZ equation in all of these models of random growth. And since then, laboratory experiments have seen the following two things. One, that Kardar, Parisi, and Zhang were correct about the qualitative universality of the KPZ equation. And two, that the calculations provided by Kardar, Parisi, and Zhang did not actually precisely agree with experimental data, with the reason for this being at a surface level that said calculations were not done sufficiently carefully. Thus, one can adopt universality of the KPZ equation as a general philosophy and get exact numerical predictions by experiment, but it turns out gathering precise experimental data is technologically very difficult. The motivation for my research is to understand Kardar, Parisi, and Zhang's calculations more carefully and thoroughly, and then mathematically explain where the discrepancy with laboratory data actually comes from. As for methods, the KPZ growth is of very high frequency nature, and ultimately the difficulty in studying KPZ growth is in understanding statistics at these very short or high frequency wavelengths. Following traditional ideas in fluid mechanics to analyze short wavelength data, my work has provided a detailed mathematical description of how short wavelength data translates into data on longer wavelengths that is much more accessible both experimentally and theoretically. So by using these methods, I've been able to provide a complete description of universality in a number of previously inaccessible random growth models, thereby giving mathematical proof of said universality. And in doing so, I have also started the development of a general mathematical mechanism to understand small-scale fluctuations in the sciences more generally. For example, in statistical models of classical fluid mechanics. To wrap this up, support from the ARCS Foundation has helped tremendously in undertaking this research project, and I am excited to continue working on this even more in the future.